The modern world is constantly generating deeply personal information. Every time you type a text message on a smartphone, every time a hospital MRI scans a patient, and every time a bank terminal flags a fraudulent transaction, highly sensitive records are created. Historically, to train an artificial intelligence on this information, data scientists had to physically move all of it. The traditional machine learning model requires taking the raw data from millions of these distinct sources and shipping it to a single, centralized server to be processed. Pooling all that information into one place creates a massive security honeypot. If a hacker breaches that single central vault, they gain access to the private texts, financial histories, and medical records of millions of people at once. Because of that risk, strict privacy laws exist. Regulations like HIPAA in healthcare and strict financial compliance rules legally forbid hospitals and banks from pooling their raw data into a shared server. The artificial intelligence industry reached a bottleneck. Developers needed a way to continuously train models on diverse global data, but they could no longer force users and institutions to surrender their raw, private information to a central vault to do it. The solution to this problem is a structural inversion called federated learning. Instead of bringing the data to the machine learning model, you bring the model directly to the data. This diagram maps the framework. The central server sends a global model to client devices. During local training, devices train the model using private data, never leaving the device. Devices upload only mathematical updates. The server aggregates these to compute a global model, restarting the cycle. This continuous four-step loop produces a highly capable collaborative intelligence, while mathematically guaranteeing that not a single raw text message, photo, or medical record ever leaves its host device. In practice, this framework operates across two distinct extremes of computing infrastructure. The first is cross-device federated learning. This involves millions of highly unreliable nodes, like smartphones that constantly drop on and off Wi-Fi networks or run out of battery. It is used primarily to train consumer features, like predictive text keyboards on mobile phones, directly from user interactions. The second is cross-silo federated learning. This relies on small networks of massive, highly reliable institutions. Think of 3 rival hospitals collaborating to train a single tumor detection model. The data stays locked behind their strict corporate firewalls, but they can still share the machine learning insights. The architecture scales effectively across both environments. It bypasses the hardware limitations of a pocket-sized mobile phone and successfully navigates the intense legal restrictions of global enterprise organizations. Keeping data decentralized solves the primary privacy problem, but it introduces immense systemic friction that engineers have to manage. Look at this visualization comparing 2 distinct data distributions. Because users behave differently, their local data is what data scientists call non-IID, or highly heterogeneous. One person might type completely differently than another, creating wildly skewed datasets. When the server attempts to mathematically average those clashing lessons together fairly, the model struggles to balance the conflicting information. Beyond the math, there are severe logistical bottlenecks. Sending heavy neural network parameters back and forth over standard, fluctuating Wi-Fi connections takes massive amounts of bandwidth. If a few devices have slow connections, it causes a straggler effect, where a handful of lagging phones can stall the entire global training round. While keeping the data physically separated protects the users, it forces engineers to fight intense mathematical and network chaos that centralized servers never have to deal with. Even without transmitting the raw data itself, vulnerabilities remain. Clever attackers can theoretically intercept a client's mathematical model update and reverse engineer it to guess the private information that produced those specific numbers. To close that loophole, developers layer on cryptographic countermeasures. Secure aggregation mathematically mixes thousands of updates together, so individual contributions become completely invisible. They also use differential privacy, which injects controlled mathematical noise into the updates to mask any specific user's footprint. But because the central server is completely blind to the raw data on the client devices, a new threat vector emerges: data poisoning. Malicious clients can intentionally generate and feed toxic updates into the network with the specific goal of ruining the global model. Then there is the risk of systemic bias. Federated learning protocols typically only select devices that are plugged into the wall and connected to fast, unmetered Wi-Fi to avoid draining a user's battery. This inadvertently excludes the data of lower-income users who might rely on older hardware or cellular data, resulting in an artificial intelligence that lacks representation from entire demographics. Federated learning is a functional alternative to centralized data hoarding, allowing us to build intelligent systems without compromising individual privacy. However, it is a mathematical framework, not a magic wand. Deploying it responsibly requires rigorous, ongoing governance to ensure that the collaborative AI we build actually protects and serves everyone equally.
If you enjoyed this video, please like, comment, and subscribe for more AI and technology content. Thanks for watching.